Hello everyone, I'm Yoihenba, and this video is going to be about differential equations and its applications in real life, starting from defining what differential equations are. Differential equations are really just equations that relates one or more unknown functions to their derivatives. For example, this is a first order differential equation, and you can obviously see our unknown function is y of x. Moving on to its applications in real life, we have its first application in kinematics, which is a branch of physics that deals with bodies under motion. For that, we use the differential equation for the acceleration vector, which is equal to the second derivative of the position vector as a function of time, which takes the following form. Here, a vector is the acceleration vector and the little r there is the position vector. Next, we have this application in finding rate of reactions in chemistry. For that, the differential equation takes this form. Here, this term right here is the rate of reaction. The R, which is enclosed inside a square brackets, is a concentration of the reactant. K is the rate constant, and the exponent N is the order of reaction. Next, we have this application in finding population sizes of organisms in biology. For that, the differential equation takes this form. Here, this term right here is the rate of change of population size. N is the population size, which is equal to R, which has a long name. It is called the intrinsic rate of natural increase, times N, the population size again. Moving on to its application in wave mechanics, which is self-descriptive. This is a differential equation about waves, which is actually a partial differential equation. And by partial differential equation, I mean that the function that we are actually differentiating is a multivalued function, by which the function is both the function of position and time. And the differential equation takes this form. Here we switch from our normal d to a curly d, which we call del, as to indicate that we are actually taking partial derivatives. Here the v in the denominator is the velocity of the wave. Next, we have this application in describing heat flow, which is again a partial differential equation of temperature as a function, and the differential equation takes this form. Here the alpha depends on the substance that we are taking, which has a name that is called the thermal diffusivity, and the differential equation looks like this. Next, we have this application in damped oscillatory motion, which is our normal, or which we call ordinary differential equation, as the function that we are is a single valued function, in this case time. And by damped oscillatory motion, I mean that the oscillation amplitude, the amplitude of the oscillation decays as a function of time, and the differential equation takes this form. It is a second order differential equation because we are taking a second order derivative of the position function x. Here gamma and omega naught are constant, which are the dampening coefficient and the angular frequency respectively. This is it for this video about differential equation and its application in real life. Thank you.